Our next speaker, Damian Gwiżdż, will be talking about optimizing C++ compilation. But before, let me introduce him a little. So, this is what Damian wants to tell us about himself. Technical leader at Nokia and a research and teaching assistant at AGH University of Science and Technology in Krakow. In my daily work at Nokia, I develop a real-time test framework written in C++ that validates 5G L2 applications. At the university, I teach programming classes. Over the years, I have taught programming in 5 different languages. Fun fact about Damian is that he has some free time, and in his free time, he's working on PhD in geophysics. He uses MPI and CUDA to parallelize seismic simulations in complex geological models. Damian, the stage is yours. Thank you very much.
It's connecting.
Okay, now? Oh, yeah. Okay, so sorry for so many difficult shortcuts, acronyms in the intro. So what I am going to talk about today is the C++ build time optimization. So there is one very familiar meme that comes to my mind when I think about the build time in C++. Yeah. So basically, this is like our only legitimate reason for slacking off at work. I guess you can, for example, get up in the morning to work, pull up the changes, and start the compilation, and then you have to wait for like 30 minutes to that finish. So today I think I will make you a bit sad. Maybe you will dislike me a bit after this talk, because I will show you how you can reduce that build time even by 2 orders of magnitude. Yeah? You can use some existing techniques for that, but you can also use one that I am going to show you. It is not that difficult. Most important will be the approach used behind it, but you will see shortly. So someone might say that there is one reason why there is a problem with the build time in C++, and people might call that skill issues, but I think that the header issues are the biggest problem. Björn said this morning that he really dislikes the preprocessor, and you will see shortly why. So this will be the first point. Then we are going to switch into talking about Unity builds, and you will see that there are massive gains from enabling them, but they are not like a silver bullet to solve all the issues. Then I will show you a part of the pointer to implementation, the pimple idiom, that can be used also to improve the build time, sometimes even without additional costs. Then some nice tricks related to the forward declaration, and finally I will show you this new thing, this low-cost data access that we have used internally at Nokia in one of the projects, and the results were like quite promising. Yeah, so to start, I have prepared this short example. It is not really important what it does, but important is that I am using, for example, a reference wrapper, which is forcing me to pull the functional include into the code. Then I am defining a vector of references, so another include. Then we are printing this to the standard output. So this simple piece of code already forced us to do 3 includes in the code. Yeah? And you might think, so what? We have the includes, those are the standard ones, so there should be no issue with them. And we can see what is the issue in the Godbolt. There is a very nice option where you can print the output from the preprocessor. And this example you can see in here that we have almost 40,000 lines of code just from those 3 includes. Yeah, very standard ones. And I have, on purpose, fixed the C++ standard to 11 and chosen the GCC, so we can do a quick experiment in here. So what I am going to do is that I am going to, keeping the same compiler, the same source code, I am going to switch to newer versions of the C++ standard. Yeah, I am going to do the same for the CLang and GCC. And then the question is, what will the plot look like? So on the x-axis, I will put the compiler versions, and then on the vertical will be the number of preprocessed lines of code. So do you think it will be like flat? It will stay that way? Is there anyone?
I think it will increase.
Yeah, so do you think it will grow? Yeah, so will the growth be linear or faster? So linear, very few people. Quadratic? Yeah, so quite a lot of you got this right, because this is how the plot looks like. So basically, it doesn't matter whether you use CLang or GCC, we can see the same trend. And I have also tried to do a bit of extrapolation from that data. So you could see that for the C++26, this can get even worse. It will most likely do, but we are not sure yet how much, yeah? And I'm still talking here about the headers. There is, modules are not used here, yeah? So you can go with modules and try to optimize also that way, but this will be not the main topic of this presentation. Okay, so now another experiment, we have seen that the number of preprocessed lines of code has grown over the C++ standard. So now I will use the build bench, another online tool, and we will see that there is a similar kind of growth in here. So we have this setup, the same code as previously. Again, doesn't matter what it does, only the fact that we have those three includes. I have set up all the combinations from the previous slide, and here we have the results, but maybe there are not so much readable in here. So let me show them like this. So this is the memory usage of the compilers. The same compiler, the same code, only difference is the C++ standard. This is the memory usage, and this is the build time. Yeah, so initially you might have thought that the lines of the preprocessed code have grown, so what, yeah? But this has real consequences. And I think that there is a like causal chain in here, because when you have more preprocessed lines of code, this like impacts how the compiler works internally. It uses a lot much memory, and this will then impact the compilation time at the very end. And of course, that is not like the full story, because I am talking here only about how much text the preprocessor gets as input. But of course, you will get a different source inside. So you can, for example, from some headers, get some heavy template instantiations into your code. Yeah. So this can be also the factor in here. But yeah, maybe to get a better look in here, some guy who is working on the compilation will have to help me a bit, yeah? So this is the idea that we have, and we have also observed this in the data. So we have internally, for example, plotted the memory usage against the preprocessed lines of code, and there is like this nice linear correlation between them, okay? So in C++, basically, with the use of those types, like for example, I used reference wrapper, but I had to include the whole functional header to get it. And yeah, and this is really wrong, because we are using just one type, but we have to pull like whole the tree from this picture. Yeah. So definitely there is no parity for this rule that we only pay what we use. This is maybe true at the runtime in C++, but at compilation time is definitely not. Okay. Okay, and then yet another online tool that you can use to do some experiments. I have used again Godbolt, but this time I have switched to Clang with the time trace flag. And what is really nice is that you can use this online tool to produce very nice charts that show you exactly what happens during the compilation. And maybe this is very detailed, but what is important in here is that this code that I have been working on, with Clang, it compiles almost 1.5 seconds. Yeah, and then we can do some modification. We can include just one header. So we can see half a second for the functional. Then we have vector, another one. We see also the time impact from this header. And finally, the IO stream, which is the heaviest one. And what is important here is that those three numbers, they do not add up. Okay, so if you compile them separately, you will get bigger time than when you compile all of them together. Yeah, and this is the main idea that is applied for the Unity builds, because you can benefit from this overlap in the headers, not only in the header files, but also in the source files, in the CPPs. Okay. Yeah, and this allows us to switch to the first topic that I wanted to cover, how you can optimize your build time, and this is the CMake Unity build. So enabling it is very simple. Basically, in the CMake, you have to specify those two options, and then the tool will do all the magic for you. But this, to demonstrate how this works, I have to get some code that is, this is also some example how the Unity build will look like internally. Yeah, so basically some sources generated which will include all other sources. Yeah, so I had to create some code that is heavy to compile, and you will see some strange things being done in there. But be sure that this is not some imaginary example. I have adapted something that we have actually had in our code base. Yeah, so keep that in mind in here. So the first thing, maybe do you know this library, Boost preprocessor? Yeah, a few people. So you will now get another tool in your belt, but please use this carefully. So basically, what I have done is that I have created this magical generate macro that will expand at compile time. Sorry, not at compile time, but during the preprocessor. It will expand to the fields and to the methods in this class. Yeah, so I can then very easily generate a lot of code. And this example here is taken from the telecom domain. You see the configuration, the cell groups, the user equipment, UEs. So those are the mobile phones that you use in our domain. Yeah, so those ones. And then the GNodeB, this is the main hardware that is used for the tests. And then the last one is 50 more of those. So it will expand just to those tuples of those types, name, and then the default at the end. Yeah. So next, maybe this one we can skip. Yeah. So in this generate macro, we use the tools from the Boost preprocessor, and the most important is this one, which basically allows us to iterate over the parameters that we'll put into that macro previously and generate some output for each of them. Yeah, so basically we're iterating in here, and then at the very end, we call this macro, which puts a private field into the type and the accessors. And here I am using the notation in which the field will have the underscore on the end, and the accessors will be exactly the name that you have provided in that macro. Yeah, and this is how this can be used later. So, for example, the field called I7 was generated. I can get the value from that field, and I can print that. Yeah. So this is the first stage of creating very heavy compilation code. Here you can see some proof that this compiles and runs. So you can play later with that Godbold link on the top. Then second thing, because this was still not enough for me, because I wanted to have something very heavy to compile, but this surprisingly was not. Yeah, so I have to try harder. so the next thing that I did, I have used the functional header. Yeah. How many of you think that this header will be heavy for compilation? Yeah, maybe few of you have burned your hands on that header because it is quite heavy. It was this one from which the reference wrapper was coming. And here the most interesting part is that what is actually heavy is the instantiation of this std function. Yeah? And what I did is that I have, apart from those fields which I have generated earlier, and for those accessors, I am now also adding some metadata. So I can then at runtime, for example, get the name of the field. Yeah. So this will be the getter and setter and the name. And again, some very magical macros, boost preprocessor, and in the final step, you are generating something like this. So basically the meta structure which will keep inside the name and the accessors, like wrapped in the lambda. Okay? And then finally, after we do that, we can access the meta. You can see, the pointer is not very visible, but you can see in the second line that we are getting the metadata from the field using the name. And then we can, for example, set the value or get it. Okay, so this was the second part, but this still managed somehow to compile on Godbolt. Yeah, even though I tried very hard. So I have to try harder to make this fail finally. So I have decided to use the tuple. And what I did is that I have put all those metadata that were generated for the separate fields into one structure. So we can then, for example, iterate over them to print all the fields in the structure. Yeah. And this is how the metadata is generated. So basically you can see in here the tuple. And this was the final nail in the coffin, because after doing that, I have expected that this print will work. Yeah, you can see in here that we are just going over all the metadata and then trying to print them using some clever lambda. Yeah, but the result was that this finally has failed on the Godbolt. Yeah, so we ran out of the resources that are allocated in there, and we got a compilation error. So I finally had code that was heavy enough to make some good examples how the Unity builds impact the build time. Yeah. Okay, so basically, it's a really happy guide after that. So we are, yeah. So this one you can see later. Yeah. So the structure that I have created that will be used in the next examples, this is again something that resembles the configuration in those tests that I am working on at work. So we have like tests for some telecom functionality, and in those tests you usually configure some cells. So this will be the area which is covered by the BTS. You configure the UIs and so on. And each of those types, remember that this is not like a contrived example. This was really used in the code. Each of those contains such macros. Those macros expanded to the use of functional. And then finally, the functionals and everything of that was wrapped into the tuple. Yeah? So you see that this is very like heavy kind of data. Yeah, so this is the structure. And then what I did is that I have decided to generate 600 source files. And those source files are very simple because basically each of them includes one of those types in here. Yeah, so for example, the configuration, the cell, and so on. And this will look something like this. Yeah, it's not sure if this is visible, but we have in the middle the configuration. And those red balls that point to it, those are the CPPs, which are, in our example, the heaviest one to compile because they like include whole the configuration tree. Yeah. The other ones, for example, the UI or the bearer and so on, those will have less dependencies than the first one. Okay, and then to maybe better visualize for you how the includes are spread out over the 600 files, I have put this into this kind of array diagram, where on the horizontal line you have like a column, the row, and then you have a formula on the top, which you can compute the number of the files. So for example, in here, you will have the file with the number 300, in here, file 500. So basically, this means that at first we have 100 files that are next to each other, and they have all the same include. Yeah. Then the next one, the next one. So basically, this looks like this. And I have tried compiling this now with the different sizes of the Unity builds, and here is the result. So basically, from like 2 minutes to build on this on 8 cores, we went down to some like in the range of 10 seconds. And this was all from just enabling the Unity builds. Yeah, but this case that I have used in here, this was really the perfect case for using Unity builds. So you have very, very well placed includes like header next to each others. Yeah, so if you like basically take 2 source files, including the Damian 1 CPP, then you will have like basically 100% of the overlap. Yeah, so this is why we see like with the increase to Unity build size 2, you can see the 2 times reduction in the build time. Okay, then another example, I have decided to maybe do this more like real life example. So instead of having all the files next to each other, I have mangled a bit the order. And now we have like this sequence. We have the 6 different headers included in 6 different files. And then this repeats and repeats and repeats. And of course, if we add to this plot that was created previously, you see again the quite well optimization, but the downward trend is not so fast at the very beginning, because this time it happens so that the headers they were not so well collocated to the next to each other. For example, you see in here that the last one, which is called bearer, should be next to the UI, so it can be reused, but it was like divided by the cell type, and this is the reason why the first data was better than the second one. Then another example, random permutation of all the data. And in this case, what do you think will happen? Where will the data be? Will it be worse than the first one? Yeah, where? Under the blue line or above the green or in the middle? What do you think? So who is for the under the blue line? Yeah, in the middle? Yeah, quite a lot. And above? Yeah, so quite a lot of hands for the option 2 and 3. So actually this is in the middle, yeah? Because in here it happens so that the distribution was quite unfavorable for Unity builds, because the files were not really that similar, and they were placed in the files next to each other. But in this case, when the files are randomly permutated, it happens that they quite often have the same include next to each other. Yeah. So this is why we see better results in here. Then the next example, and this is where the things start to be interesting. I have added basically empty CPP files between those which have the heavy includes. Yeah. And the result of that is that basically so this is taken, this is as the baseline, so this like greenish line, and then we are adding empty files, and you can see that this greenish line like moves to this side, yeah. So next example, this may be not so well to read, but you have like 2 empty files, between each file that has some include. And now again, we are moving to the right. Yeah, now another additional one. Yeah, and we see the trend. So you increase the number of source files that do not have the related header, and then the gain from the Unity builds start to diminish. Yeah, so the main takeaway from this is that you will gain a lot of benefits from using Unity builds, but you have to have two conditions fulfilled. You have to have like very densely included headers in the CPPs, so there is actually the overlap. Yeah, and you have to have actually something that is heavy to compile, as I have showed you previously, because yeah, in this example, you've seen that I have added empty files between those, which are heavy. But if these source files there were also heavy, then you will get some drawbacks, because you will now compile a lot more in one CPP, and this might actually not scale. Yeah. So if you have like one CPP with 10 different types which are heavy compiled, then this will at least add up. And maybe it will also grow like more fast than just the linear trend. Yeah. So this was the one approach in which we have the Unity builds enabled with different combinations. But of course, you can also try doing some brute force on this stuff. So you can try to increase the number of cores. So I have actually measured all those combinations. So there was like a very nice script that I have started on Friday when leaving the work, and it has finished on Monday. And it has built through all the different combinations. So you see that increasing the number of cores basically almost drops in half, but the shape of this data still remains similar to what was at the beginning. And again, I still have some spare cores on that machine, so another increase to 24 cores and then to 32. So we are at the level of 30% of the original time. Yeah. In the perfect case, we will go down to the 25%. So we are very close. And finally, I have used all the cores on the machine, and we are around what we expect from this, like multiplying the number of cores by 4. Yeah. So this is at what stage I have ended up after just using the Unity builds and putting more cores to the build. So at the level of 55 seconds at the top from the original one for over 120. And then I have started doing some other tweaks into the code. So first one that is actually quite simple to use is to try hiding some of the implementation details in the types that you have. So for example, in here, you can see that we have the GNodeB field in the configuration, and it is initialized directly in here. So this forces us to include the full type definition, so we can initialize that field. And what we can do is that we can wrap that field into a unique pointer. And if we do that, you will see that the details of those GNodeB types, they can be hidden in a CPP file. Yeah. The only condition when you can do that is that you have to provide some constructors and destructors in the type itself, because if the constructor is still in the header, then it will force you to do the full inclusion. Yeah. So you can hide it in this example, and then of course include the full type definition in the CPP. Okay. Another example, maybe not so obvious as the previous one, is that you can actually, with some types, you can use the forward declaration, and you do not have to include the full type definition. So in here you can see that we have a vector. Yeah, and this vector actually, until you use the members like the size or access the elements, you do not have to include the full type. Yeah. So this is like a very nice trick that you can do in your code to also hide the dependencies. So this is basically for free if you have vectors in your configuration tree, for example, like in my case. Yeah. Okay, and then similarly as for the unique pointer, if you do that, you have to hide the initialization into the CPP file, so the constructor and destructor does not force you to do the inclusion of the full type. Yeah, and then the rest of the code. So I have done the modification with the pimple idiom. So this was how the code looked like initially with the direct access to the member, then to the field, some assignment, and we had only one inclusion in here. But after doing those modifications, you can see that the number of includes has grown. And you might have thought that maybe this is worse, but it's actually better because we now have more control over what we actually include in the code. And if you, for example, do not want to modify the fields under the Gnode B, then you do not have to include it at all, and you do not pay for that at the compilation time. Yeah. And then in the final example that I have put on Godbolt, we have those additional CPPs which has to be added to support this kind of pimple idiom. And I have also added some of the forward declarations for the types which I have used that way. So there is this nice convention when you prefix the HPP with FWD for the forward declarations. Okay, so this was the result that we had previously. With the pimple idiom enabled, we went down another 30% over, yeah? So this is how we ended up before this new technique that I wanted to show you. So, yeah. But before that, yeah, one more thing, because you have seen that I have defined some of the forward declarations in here, but there were more types in the configuration tree previously. And what is missing is here are the forward declaration for the vector-like types. So for example, I had a list of the UEs, not just one. So I had to also somehow make the forward declaration for that. And there is a trick which we can use, because just doing a forward declaration for something like this, it is very tricky, because this is a template which has a default value for the allocator. So you cannot simply forward declare that type without explicitly putting the second template parameter in there. So you could do that, but then you have to always provide the allocator in the code, so it will be very inconvenient. So in here, what we did to get the forward declaration for the vector was actually something that is often forbidden by the guidelines, by simply inheriting from the STL container. You can give a type, not just using, like previously, alias for the type, but you can create another type for this given one. So you can then just forward declare it. Yeah, and by that, I have like complete list of all the forward declaration for all the types that were used in my configuration tree. Okay, and now finally to this new techniques, because yeah, the stuff that I have shown you previously was like the necessary background, because we have seen that we have used all the like tools that we have in our belt. We have put more cores on it. We have used Unity builds. We have tried some like hiding of the dependencies and so on. But now we want something even better. So on this chart, you can see that there is like a spectrum of how heavy given include is. So on the green side, we have the forward declarations, which are basically free. And then on the other side, we have the headers, which can be very heavy. And what we did is that we have introduced something in the middle that will be very lightweight. And we actually wanted this to be as fast as the forward declaration. So basically, we can use this for free in the code. Yeah, but we can still access the data in the structure. So this is the motivation, and this is how the use of the LCDA looks like. So first I will show you how you define some accessors, and then you will see how it is implemented. So at the top, there is an include to the library, followed with some forward declaration, and this is very important because those are only the forward declaration. We try to not include anything other in here. And at the very end, we are declaring the accessors that can be used. So for example, from the configuration, you can get the GNodeB field, yeah, or you can get this I7 integer. So we have the header, and then you have also the CPP, which is implementing those accessors. Yeah, so there is a pair, header and CPP. Okay, the structure is here similar. So we have the implementation header. We here include the full type definition. So this is the heavy header. And in here, the macros which are used to implement all these magical accessors. And what happens later in the code, this is something that you have to get used to, because we are switching from this syntax where we are calling methods on objects into something different. Yeah, so there are two changes in here. You see, previously there was a configuration included. Yeah, and the fields accessed. Now you have the LCDA header and this LCDA macro under the includes. And what is actually also interesting is that we had to add more includes after changing that. Initially we had the full type. Now we have only this LCDA header, which doesn't have the information about the types which are deeply in the tree. We have only the top level, so you have to include them explicitly if you want to use them. But the benefit from doing this is that there is no longer the include to the configuration in this file. Okay. Yeah, and then this is how this looks on Gwiżdż. So you can take a look at this small library that I have added in there, the decal, impl, and there is also one like helper file, and then we are adding those two. The header for the LCDA and the CPP. Okay, and of course you can use this also on the containers. We have a specific macro for the declaration in here, but the idea here is similar, that you only include the forward declarations of the element and the container, and you define the accessors. In this case, it will automatically expand like to some add functions, the size, and so on. Yeah, and then the similar thing in the CPP. So you have the full type inclusion in the CPP, the forward declarations in the header. Yeah, and now going back to this small example, this is the state before the LCDA was applied for the container. You see the normal calls to the add methods. When doing the migration, you have to shuffle some braces, yeah? Instead of calling add, we are adding this kind of call to the macro. And you see that this is very incremental. You can migrate one type at one type at time, yeah? And you do not have to do this all at once. Yeah, and then the final one, this is where the migration was completed, is that this was the state before, and this is the state after. Yeah, so this is like very trivial conversion in the code, but you have to get used to it. But if you do it, then none of those types which are actually used in here are included in the CPP file. Yeah, because everything is hidden behind the forward declaration, and you only use those accessors. Yeah. So there is the complete type in here. And now how this works. So the decal from here, this basically expands to a function declaration prefixed with this LCDA at the beginning, and this is actually very crucial, you see in a moment. So very simple thing. If compiler sees that macro in the code, it will like immediately expand this to the function declaration. So this is very lightweight to compile. The implementation, also very simple. You generate those functions which corresponds to what was defined in the header. Yeah, so you can then provide the implementations for the compiler. And finally, those strangely looking, that strange looking syntax with the LCDA macro, this is actually done for one single purpose. So we can write the expression from left to right instead of the another way around. Yeah, so this second example in here, you see that we are starting from calling add, then cells, then again add, and so on. But this one is much more readable. Yeah, but under the hood, under this macro, we are only adding like simple function calls. And the reason behind this is again to not force compiler to do any work. We are expanding to function calls, and then compiler will just go through them as if there was nothing to do actually in the code. Yeah. And there is also another trick, because sometimes you might not want to have this function call overhead in your code. So this can be actually quite easily achieved. Only thing you have to do is just to include the implementation of those accessors somewhere in the code. Yeah. So we go from this, from the header of the LCDA, we include the CPP, and in the CPP, when this flag is enabled, the code that is generated will be slightly changed. So we will put the inline at the beginning. Okay, and I have actually also measured that. We have the test framework internally using like both of those approaches, and there is basically like no approach because the compiler is quite. This is quite light for the compiler to inline. Yeah, so easy to inline, easy to compile, and the result from doing that, this is the initial build time using like the 8 cores without this approach and without also the pimple things that we did previously, and this is how it looks with this LCDA approach applied. So you see, basically, Unity build size 2, and we are already done. Yeah, and only on 8 cores. Yeah, we went down from 136 seconds down to 11. And if you even wanted to regain all the performance in the code by eliminating the function calls, you can enable the LTO. And you see that only like 2 seconds were added to the example in here. Yeah. So this is how this looks like. And another example, this might be also quite illustrative because I have shown you here the time that is visible for the user. So from the time he starts the command until he gets the results. But also what is important is how actually the machine is loaded. So we have the user time from all those parallel compilations, 920 seconds. We go down by 95%, yeah, by using this technique. So basically, all the work that the compiler had to do in the CPPs, it disappears because basically you are almost including nothing from those heavy headers. And then the total build, only 5% of the original one. And what is interesting, after enabling LTO in here, it went even down. Yeah, so this was quite surprising for me, but probably the compiler, when the LTO is enabled, is doing a bit less work during the compilation and is shifting that to the link time. Yes, so if you look at the user time, it will reduce it, but if you look at the real time, it will bump it up a bit, yeah, because the LTO phase might be quite long. Yeah, this will depend on how your code looks like. Yeah, so basically, this simple modifications, and we get the 150 times speed up. So this is the 2 orders of magnitude that I have promised you at the beginning. And some other examples maybe to also show you why the gains are so heavy. This is how the configuration types look like, and we see the inclusion at the level 0. Then at the level 1, it starts to becoming interesting. Level 2, 3, 4, and 5. Yeah, and I stopped in here those two blobs that you see in here, this one on the right, this is the boost preprocessor library, and on the left you have the standard library. Yeah, all those dependencies that are pulled into the project. And now, this other approach, we have the LCDA header. We include the forward declaration from it, and basically at the level of 2 we are finishing. And this is like very lightweight because of that. And the final table that I have created for you, those are data from one of our internal tools that we are used to measure the compilation time, and it is able to collect some quite nice statistics at the level of headers. So you can see, for example, that the configuration previously was taking almost 800 megabytes to compile, and this LCDA version, from which you can again get the same data, is almost 400 times faster. Yeah, so sorry, not faster, but less memory that is used. Yeah, yeah. For the build time, this was how the header contributed to the total build time before and after. Actually, the tool did not manage to even measure that, so I couldn't guess what was the speed up, but this was probably quite big. And the final one, this is probably the statistic that is the easiest one to get. Is the number of preprocessed lines. So we are going from 40,000 to just 30. Yeah, at the end, by just using this technique. Okay, so thank you. I guess you can try. Maybe you will see similar results in your projects. So thank you.
Do you have any questions? Okay, we have a question there. Perfect.
Did you consider adding this solution directly to the compiler to avoid affecting code syntax?
Not yet, but I think that there might be actually a thing that could help. Because if we had that unified function called syntax in C++, where you can define the methods on the type, not in the type, but outside of it, then instead of defining the accessor as separate functions, we could define them actually as those methods which will be added to the type, and then there will be no change in the syntax. Yeah. So this is the kind of thing that I hope for the C++ to add in the future.
Good luck.
Any other questions? Okay, I guess not. So thank you once again.
Thanks.